Okay, good morning, ladies and gentlemen. Today there's going to be zero homework for today. Basically, all we're doing is we're kind of introducing to what's called a definite integral, which in the end you're going to find out, hopefully over the next few days. Definite integral is our function that accumulates area under a curve, and it's just kind of baby steps through this. And this first thing we're going to do here is we're going to call it counting squares, and you're going to understand what hopefully this accumulating area is. Now, I have two of them. The first one we're on is 5.0b, which is the truck velocity problem, and the volume of a football is at the end. It's the first page on your note sheet. And as you're going through there, it says, as you drive on the highway, you accelerate to 100 feet per second to pass a truck. After you have passed, you slow down to a more moderate 60 feet per second. The diagram shows the graph of your velocity, v of t, as a function of the number of seconds, t, since you started slowing. So this graph is showing my velocity. So bottom line, I'm looking and I can see my velocity is right up here at time 0. I accelerated 100, I let off the accelerator, and my velocity curve is kind of slowing down until I come down to a certain point, and then I'm constantly going at my moderate 60 feet per second. Well, think about it. How is velocity rated? Well, so because my velocity is my y-graph, this is going to be feet per second, and my x-axis is going to be in seconds, okay? So what we're going to be doing here is we're looking at this, and number one says, what does your velocity seem to be between t equals 30 and 50 seconds? Well, and then how far do you travel? Well, if we're looking here, we're between 30 and 60 seconds. It sure appears my velocity is 60 feet per second. So this is, how far do you travel over the time interval, 30 to 50? It sure looks like I'm going a constant velocity there. And even back in Algebra 1, we had this distance equals rate times time, to where my distance equals my rate of 60 feet per second times my time. Well, the time interval between 30 to 50 would be 20 seconds. Well, my distance obviously is going to be what? 1,200 feet. Not a big deal, and I can kind of look at that. And then it says number 2, and I'm going to go fuchsia here for number 2. Number 2 says, explain why the answer to problem 1 can be expressed or can be represented as the area of a rectangular region of the graph and shade the region. Well, that is because I'm looking for from my 30 seconds here all the way over to my 50 seconds here, because that looks like I'm pretty much going at a constant rate, okay? This area right here, okay, that's the area we're talking about. And if I looked at this, well, they're kind of different units. When we're finding area, we're typically used to making sure everything is in inches or in feet or it is in miles and stuff like that. But here it's a little bit different, because when I look at my rectangle, okay, I can see the width of my rectangle is 20 seconds, and the height of my rectangle, if I want to think about that, is I can see that's 60, but that's in feet per second, okay? And when I do this, it's kind of cool, because I can look at my units up before. When I take 60 feet per second, and I take that times 20 seconds over 1, I can see my units reduce, and that's going to give me my 1,200 feet. Okay, so now we're going to be accumulating area underneath a curve where my units aren't the same. But notice my units are usually pretty close to where I can cancel them out and I'm going to have a single unit in the end, all right? And we're going to be accumulating areas for velocity and acceleration, all kinds of different stuff over the course of the problem here, or the course of the year. And now we're going to move on to number 3. And number 3 basically says, okay, the distance you travel between t equals 0 and t equals 20 can also be represented as the area of a region bounded by the curve or our graph. Well, that means, because when I'm going from 0 here, all the way over to, where am I going? 0 to 20. I'm basically looking for the area bound underneath this curve. And there's a little technique here. And what it does is it says, count the number of squares in this region, estimate the area for parts of squares to the nearest 10th square space. Okay? For instance, how would you count this partial square? Well, that's this little guy right here. And everybody's going to do this different. Please understand, everybody may or may not get the exact same answer. It's okay. We're estimating now. We're all going to be relatively close. But when we're estimating by squares, well, sometimes I would look at this and I would cut it diagonally. And I would say, well, that top piece in the right up here, if I took some of that away, it's going to fill this bottom. But it's more than half, so I'd probably round that off at like 0.6 for that square. Or other times I might not cut it diagonally like that, and it's just an estimation. I might try to cut it in half this way. But either way, I'm doing the same thing, and I can cut this little sliver off right there, and that's going to fill this top piece. You know, I'm not going to put an obnoxious amount of time and agony over, oh, is it 0.6, is it 0.7? I don't really care. I know it's more than half, and it certainly doesn't look like it's 3/4 to me, because if it were 3/4 to me, well, then I would be slicing it here, roughly. It's kind of a crooked line, but there's not enough here to fill all that. So there's no way I'm going to be, you know, going up to 0.8, in my opinion, but it's just how we're going to do this, okay? So we're going to estimate these by counting squares. And we're going to be estimating underneath this region right here. So my blue scribed region. This is a skill you're going to have for your AP test, okay? You might not use it in a graph. You might just use it in a table of values with data. So what I would like you to do is I would like you to count the approximation of squares, okay? I'll go through this one with you. So for my number 3, I'm just counting squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So I have 25 full squares. Plus, now I'm going to approximate how much of each square that I have sitting there yet, okay? And it doesn't matter where you go, top to bottom. And I'm going to look at this top little piece. I'm going to call this little niblet here, I'm going to call it 0.2, because it looks like it's, you know, and here's my thought. If I diagonally came across there, okay, it's definitely less than half, but it's definitely looks to me like it's about half of the half, but not more than half of that. So that's why I'm going to 0.2, okay? And just go through and estimate the rest of these. And tell me what you come up with, and we'll go from there, and I'm going to estimate the rest of mine, and I'll be back in a second. Okay, so I came back to mine, and I kind of wrote with a little line to each little section of each one, except I did miss one. This one I'm going to call 0.9 as well. Then I'm just going to add those all up. And what do I get? I get 0.8, 0.9 is 1.7, is 1.9, is 2.8, is 3.4, is about 3.6, I think I'm coming, plus 3.6 more when I add up all those partial squares, which is actually, in the end, this is going to equal for me, this is going to equal 28.6 squares, okay? And that's when I'm counting my squares. Now, the next part here, it says in point 4, or not point 4, number 4. Number 4 says, how many feet does each small square on the graph represent? Well, if I take this little square here, and I make a square, well, I can see my bottom unit, well, from here to here, well, that looks like that's 5 seconds, okay? And vertically, I'm going 10, 20, no, I'm 10, 20, 30, 40, 50, 60. So this is 10 feet per second. So each square actually represents 50 feet, right? And it's 50 feet per square. This is kind of the neat thing with units. So I have 50 feet per square. Okay, so if each square is 50 feet, and they want me to estimate with squares how far you traveled, well, I'm just going to be taking my 28.6 squares times my 50 feet per square. What does that equal? I can see my units of squares fall out. 28.6 times 50. Well, if I took it times 100, that's 2860 divided by 2. That would be 1,430 feet is what it appears we traveled there. Okay? And number 5, okay, that's estimating with my square. Notice each square, it's not a square unit. Each square in this application, because I'm velocity compared to time, which is feet per second times seconds, each square represents 50 feet travel, okay? Each square represents 50 feet per square times my squares. Total number of squares gives me my distance traveled. Well, number 5 says problems 3 and 4 involve finding the product of the x value and the y value for a function where y may vary with x. Such a product is called the definite integral of y with respect to x. Based on the units of t and v of t, explain why the definite integral v of t with respect to t in problem 4 has feet for its units. Well, it's pretty easy to see, because as I'm taking my feet per second, okay, that's my y value, and I take that times my seconds, that's my x value, and if I multiply them, well, feet per second times seconds gives me feet. Therefore, any time in this particular picture, I'm going to get feet when I multiply and get an area underneath that curve, okay? And these units are going to be different on everything, but that's the whole process of a definite integral, okay? A definite integral, each square underneath this curve, each square accumulates distance. And this is what a definite integral does. A definite integral is an area accumulator underneath the curve, okay? And things can be different. So a little small note, I don't think this is I know this isn't in your notes, but the area could represent any type of quantity based on the units of the independent and dependent variable, okay? So every time we're going underneath the curve, the area is going to equal the y value times a change in x, okay? That's going to give us an area. And where is this ever used in the real world? Well, everybody at home has a thing called an electrical bill, okay? And if you look at your electric bill, they usually have little graphs per month and stuff. But if I think about that, if I'm thinking of kilowatts on my y-axis and hours on my x-axis, okay, if I had a curve here, I could accumulate the area underneath this curve. And if I accumulated the area underneath that curve, it would be kilowatts times hours, and those are kilowatt hours. Okay? And kilowatt hours are how they explain your bills. Kilowatts, kilowatt hours. And it's kind of a goofy thing, but that's actually how the electric company, they don't write kW hours. It's usually kilowatt hours. That's how the electric company sells electricity to your house. And there's numerous different examples that we can use to accumulate area underneath this curve. Okay? And we're going to go to the second part here. This is technically number 6. And right here, the graph shows the cross-sectional area, okay, y square inches. So y is in square inches. This is area. So this is in inches squared, okay, of a football as a function of the distance x inches. So x is in inches, okay, from one of its ends. Estimate the definite integral of y with respect to x. Okay, well, let me tell you what this really is. Okay, this is basically, if I had a football, I'm going to do my best to draw a football. Okay, and I'm not a good drawer, but that's a pretty sweet little football we got there. And actually I don't want to do it there. I'm going to try to parallel it here to our graph. And my football is not going to be very good with respect to my graph here, so bear with me. But I'm going to say here's my football's end, and this is, that's a crappy football. I'm going to be back. I'm going to draw it. Okay, I'm back. So basically, this is not drawn to scale at all, but I'm just trying to get, they're saying the overall length of a football is 12 inches. And what this is saying is, anywhere I take the cross-sectional area, so this is 1 inch. If I came 1 inch, bottom line, if I cross-sectioned it there at the tip, there's 0 area at the tip because it's a point, okay? But if I took the cross-section, if I took a knife and I cut this football right there, and I turned it so I could see the cross-section, every cross-sectional area of a football basically is going to be a circle, right? And it's saying the area of that cross-section at 1 inch, well, it's going to be right about there, which is about 7.5 square inches. And obviously, as I go deeper in, like if I came here and I cut it at 3 inches, the cross-sectional circle, when I folded it over, this graph is saying the cross-section, the area of the circle that I cut out is going to be about, I don't know, what is that, about 20, that's 25, maybe 21 square inches. Okay, so that's what this whole thing is talking about, is the cross-sectional area. And if I added all of these areas up, okay, all the way through here, even between my inches, okay, there's a whole bunch. If I found all these cross-sectional areas, and even more than I drew, and I summed them all up, this is going to give me basically, what's that going to give me? That's going to give the volume of the football. So, how do I know that? Not because I'm smart, just because it makes sense to me, and hopefully it makes sense to you too. So, what we're going to be doing here is, we're going to estimate, okay, the definite integral of y with respect to x. So we're going to do counting squares again, but check this out. This one's kind of pretty sweet, because if I cut it right down the middle here, it's 6, okay? It's really nice and symmetrical, isn't it? So let's cut it in half, and if we find the number of squares on this side, all we have to do is take it times 2, and then we would have the number of total squares underneath it. So why don't you hit pause, and why don't you go through and count the squares, and we're going to be back and we're going to compare our square counting abilities. Okay, so I came through here, and another thing with adding, with counting your squares, another strategy of doing this that I like to do sometimes is, what I'm doing here is, you see this little niblet right here that's underneath the curve, if I took this little niblet here and I placed it down inside there, if I put that piece in here, that's going to make this square right here a full square. So I'm counting that all as 1 when I put that little piece on there. So when I go across there, I'm going to have, there's 1, there's 2, there's 2.1, is 2.7, is 2.9, is 3.5, I think is what I'm coming up with in my squares. So I'm going to add another 3.5 squares. This is going to give me, what is that? 21.5 squares. Did I do that right? There's 1, 2, 3.1. Nope, there's 4 because I forgot to add that 1. So here's 1, 2.5. It's 3.1. It's 3.7. It's 3.9. It's 4.5 squares. Sorry, that's just bad counting of squares. 4.5. So that's going to add up 18 holes, and then my 4.5 parcels is going to give me 22.5 squares. Remember, that's half of that. So if I take that times 2, I'm actually going to come up with a total of 45 squares. Okay, so I have 45 squares of area. Well, if I'm estimating by squares, I also need to know how much each square represents. Well, I can see the bottom of a square represents 1 inch, and I can see the side of a square represents 5 inches squared, because that's an area, inches squared. So each 1 inch times 5 inches squared is going to be 5 inches cubed per square. So each square is going to be 5 inches cubed. Notice my units don't have to reduce like they did the other one. I'm multiplying them. I might not have fractions to where they're going to go out. So if I take the area times inches, cross-sectional area times inches across a football, that's going to give me cubic units. That's talking about volume. But if I came down here and I took my 45 squares times my 5 inches cubed per square, that is going to give me, what, 225 inches cubed would be in there. And number 7, that was all number 6 that we just did there, sorry. And number 7 says, what are the units for the definite integral in problem 6? Inches cubed. We already did that. And what, therefore, do you suppose the definite integral in this situation represents? It represents the volume of the football. Okay, so it's the volume of a football. But notice, each square accumulated volume in this case. Okay, so the area of each square, the area of all of these accumulated, all the accumulated area underneath that curve turns into volume in this case, but it's an area accumulator is a definite integral. Okay, now the next one we're going to do is we're going to come to elevata. We're not going to do all of these, so I'm going to grab my other note sheet here. We're only going to do a few of the problems in here, and then we're done. Okay? Okay, so this is the second note sheet that you guys have in your packet there. I don't know if I have them front to back or not. I think they're each separate. This is the rocket problem. And it says, Elevator, Darth's daughter, is driving in her rocket ship. At time t equals 0 minutes, she fires her rocket engine. The ship speeds up for a while, then slows down as Alderon's gravity takes its effect. The graph of her velocity, v of t, okay, in miles per minute, okay, miles per minute is shown below. Well, this is my velocity is given in miles per minute, so my x-axis must be in minutes this time, right? Because she fired her engine. T equals 0. T equals 0. So this is my t-axis, and that's in minutes, it told me. Okay. what mathematical concept would be used to estimate the distance Ella goes between t equals 0 and t equals 8? So what mathematical concept is going to represent t equals 0, 5, 6, 7, 8 to t equals 8? What mathematical concept, in number 1, would be used to estimate the distance Ella goes between t equals 0 and t equals 8? That's right. Definite integral, because I will be accumulating area underneath here. And we're going to do elevators with 2 different techniques, okay? So the first thing we're going to do is I would like you to hit pause, because the first one in number 2 is you are going to estimate the distance elevator went in squares. So we need to estimate how many squares are underneath the curve from 0 to 8. Okay, so I'm going to have you hit pause, and hopefully you're doing this, because if you're like, I'm never going to do this again, you're wrong. You're going to be doing it on your next test. So make sure you know how to estimate by squares. Okay, so I went through and I estimated. You can hit pause now and you can see how I've estimated all these. I took this little niblet here and I flipped it down into here. You can do that as many times as you want. And then I added up all my partial squares and I came up with an extra 8.8 squares. So personally for me, I counted an extra 60.8, or a total of 60.8 squares. Well, before I can estimate the distance Ella went, I need to be able to know, what does each square represent? Well, if I have a square in this diagram, each square is 1 minute, right, by 25, okay, miles per minute, 25 miles per minute, which means each square will represent 25 miles per square. And if I took my 60.8 squares times my 25 miles per square, and I multiply them together, what I came up with is Ella traveled 1,520 miles. Okay? I might be too heavy, I might be too little, but I'm going to be pretty close, okay? I think I'm going to be relatively close to what I had there. Now, Ella figures, number 3, Ella figures that her velocity is given by, so she's estimating this curve that she's got there, she's estimating that curve to be v of t equals t cubed minus 21 t squared plus 100t plus 110. Plot this on your grapher. Does the graph confirm or refute what Ella figures? Tell how you arrive at your conclusion. So why don't you grab your graphing calculator and plot that in there and let me know what you think. Okay, so what I did is I plotted that in there and I changed my windows, which you would want to change the windows roughly to be looking at what you're looking at in this graph. And I changed my limits, or my x values. I went from -1 to 12 and I put my x scale at 1. In my y, I went from -25 to 275, because I could kind of read, you can read the graph you're looking at there, and I just want the same windows. And there's one thing you guys might not know how to do. And if you go, you can lay the grid lines back on here. And if you go to Menu, View, and say, I think it's Grid, and then hit 3 Aligned Grid, it puts the grids on there for you as well. So you can kind of look at your estimation of the curve that was on the page to this curve. And although it's not exact the same, okay, there's a couple discrepancies in here, very minor discrepancies, and it's just over copying the graph from a PDF onto other stuff here, but basically looks pretty good. and we can say, yeah, I think we're having a pretty decent thing, or a pretty good looking graph. So we can kind of be confident a little bit in our estimation. And what we're going to do next is number 6. We are going to take that same graph again, and I have the luxury, I have another graph. And what we're going to do is we're going to divide the region from t equals 0 to t equals 8. So we're going to go from 0 to our t equals 8. And we're going to divide that, which represents the distance, into 4 vertical strips of equal width. So basically, 8 divided by 4 would be 2. So I'm making this into 4 equal vertical strips. So I'm going to have one going up at 2, and I'm going to have one coming down here at 4. And then I'm going to have one here at 6 coming up. And then 8 coming up. So I've divided that into 4 equal strips. And I don't like that middle one, so I'm putting a new one on here at 4. And I'm going to come here at 4. And then what we're going to do is these 4, we're going to make these 4 into trapezoids. So they're going to be connected across the bottom here. And then what we're going to do is we're going to connect this strip to this strip, this one to this one. We're going to connect this. So we have, I'm a little low there, sorry. Get that guy back on there. We're going to come up. Calibration is fun. And what we're going to do is we're going to estimate this distance now by finding the area of these trapezoids. And a little bit, this is also going to be something you'll be expected to do on the AP test. And remember, a trapezoid, okay, when we're talking about trapezoids in calculus, our height is always going to be the perpendicular distance between our first base and our second base. And the area of a trapezoid equals 1/2 times the height times base 1 plus base 2. I don't know if you remember that or not. That's a formula that I don't know that the AP board would possibly give you, but trapezoids we're going to use a lot, so they're going to expect you to probably know that. And we're going to find the area of these 3 trapezoids to estimate the distance L and when. Well, the area underneath that curve, that's going to be trapezoid 1 plus trapezoid 2 plus trapezoid 3 plus trapezoid 4. Okay? And in order to find how tall each base is on our trapezoid, that's why we graphed it in our calculator, okay? Because we're not going to, for this one, we're not going to estimate. We want to know what is this, what is this, what are these points, how tall are each of these legs. So we're going to do that in our calculator. And the way we're going to do that is we're going to go menu, trace, and we're going to trace the graph. And we want to trace the graph at 0. And then remember, if you hit enter twice, it's going to drop the dot. I want it at 2, and I want it at, not 3. I want it at 2, I want it at 4. I want it at 6. And I want to know my height at 8. Not my height, but my trapezoid. Come on. Then I'm going to come out of there. So I have this one's 110, 34. And basically what we're doing here is we're taking our trapezoid. So we know this trapezoid right here. I'm going to do that in a different color. This trapezoid right here at 2. Okay. So we know this is 110 tall. This is 234. And then we're going to come across to this one. And then we're going to come across to this one. And we're going to come across to this one nice and straight. Whoa. And this is 78. This is 170. This is 238. And I'm just going to translate. So we're finding the height, or the how tall each leg or each base is, not height, with the graphing calculator, just for a little bit more accuracy, I guess, is what we're going to do. So we know that, where did I write that down? Okay, so we know this. So we know this is going to be 110. I'm going to do that in a different color again. This is going to be 110. This is 234. This is 238. This is 170. And this is 78. And I just want to lay this out nice and slow for you, because when we actually get into the trapezoid rule, some people are going to be really confused. But this is what we're focusing on, okay? So if we took the trapezoid number 1, these are all a height of 2 because they're equal distance, and that's typically what we do. So we're going to say our area is going to equal 1/2 times the height. Now this first base is going to be 110 plus 234. Plus, that's just trapezoid number 1. Trapezoid number 2 is going to be 1/2 times 2. There's a base. Here's the other base. Okay? Plus, and we're going to come to trapezoid number 3. And that's going to be 1/2 times the height times 238 plus 170. And all the trapezoid does is it averages those two bases out by dividing the bases by 2, and it's turning them into a rectangle, okay? And the last one we're going to do, I'm going to do it in blue. That's going to be 1/2 times height times 170 plus 78. And these look like they're very monotonous calculations, okay? Now, what I really want you to focus on here is I really want you to focus on there is a greatest common factor, because a trapezoid rule is going to be written out in a couple chapters, in a few sections, a lot differently. But notice every one of these has 1/2 times height. So my area technically equals, when I shortcut this, times 2. And then all I'm doing is this is 110 plus 234 plus 234 plus 238 plus 238 plus 170 plus 170 plus 78. And you're saying, oh, why did you write out 234 a couple times? Well, it's going to modify even more. So the trapezoid is going to be times 2 times 110 plus 2 times 234. And it's going to sound really wonky and different, but that puts those two together, plus 2 times 238 plus 2 times 170 plus 78, okay? So just notice there's an ease of calculations with the trapezoids, and if you're asking why, well, why can I pull it all out? Well, the height is the same for all of them, and it's 1/2 the height, because that's why I did equal widths or equal heights here. That was the point. And if you think about it, this 110, that leg was used one time for the first one, but this 234 was used for trapezoid number 1 and number 2. That's why there's 2 of them there. And 238 was used for number 2 and number 3. That's why there's 2 of them there. I didn't want to circle that. That's why there's 2 of those there. And for trapezoid number 4, okay, 170 was also used twice. But see, these end legs, 78 was only used once, okay? So that really eases up our calculations, so we don't have to write it all out like this. Pretty quick, you're just going to jump square into this formula right here, and it's going to come out. It's not there yet. So what is the area? When I crunch that all, the area, when I take 1/2, this is really nice. Those cancel out. That doesn't always happen. But when I put all that stuff together, I get 1,472 miles. And when I'm thinking miles here, yep, I got miles there. So basically, off of the function, it's showing she traveled 1,472 miles. Our estimate using squares was 1,520. Yeah, they're pretty close. But what's going to do is we're going to end up getting the exact precise area one of these days underneath it. Okay? So that was number 4 we estimated using trapezoids. Now, number 5, 6, and 7 we're not going to do because that was not set up for the CAS calculator. It's set up for the TI-89, which we don't use anymore. So we're going to go to number 8. And number 8 says, what is the fastest that Ella went? Okay, number 8. What is the fastest that Ella went? Well, if I come back to my graph, I'm thinking the fastest that she went, the fastest that she went is right up there, isn't it? If that's my velocity, her highest velocity is her highest speed. So what I'm going to do is I'm going to tell the calculator to please analyze that graph and find that maximum from there to there. And her maximum was right there. Now I'm going to grab my eraser, get rid of all this red. And I'm going to move this point down here and this point down here. So what was the fastest that she went? Well, looks like the fastest that she went was about 248 miles per hour, right? 248 miles per minute, excuse me. She was really booking it. So, number 8 was just 248 miles per minute. She's really humming. And number 7 says, okay, at what time, at t equals 3, roughly, approximately that at approximately 3. I'm not going to take the time to round that to 3 decimal places right now. Probably should, but you can see what it is. 3.042 seconds. And number 9 says, approximately what was Ella's rate of change of velocity when t equals 5? Well, her rate of change of velocity, if this is the velocity curve, they're saying what is the instantaneous rate of velocity at t equals 5? Well, that's telling me to go to my calculator, analyze the graph. I need the derivative of velocity at point 5 at a specific point. And it looks like that would be negative 35 feet per second squared, because that is actually going to be number 9. Okay, Mr. Rookie needs to come back for that. That is actually asking us what is v prime of 5, the derivative of 5. So the derivative of velocity, that's giving us negative 35 miles per minute over 1 minute in the end, right? So that's why it's negative 35 miles per minute squared, because actually the derivative of velocity is acceleration. Her rate of change is negative 35 miles per minute. Okay, so that's why it's per minute squared. And is she speeding up or slowing down at that time? Well, v prime of 5 is giving me my acceleration at 5, which means v prime of 5 equals a of basically 5. Okay, it's my acceleration at 5, which means acceleration is negative, and v of t is positive because it's a negative slope there. And if velocity and acceleration have opposite signs, she's slowing down is one way to see it. Or the other way to see it is because she's up here and she's moving toward the x-axis at that point, she's decreasing, okay? because she's moving toward the x-axis on velocity, that also means she's slowing down. Remember, moving toward the x-axis on velocity slows down. Moving away from the x-axis on velocity speeds up. And then the last question here is, at what time does Ella stop? Well, based on my graph here, looks like Ella stopped right there, doesn't it? Looks like her velocity is 0. That should mean she stopped. And that would be at t equals 11. And based on the graph, does she stop abruptly or gradually? Well, I would definitely say gradually, because she's starting here and she's slowing down, and then slowing down even less and less and less and less, and stop. She gradually slowed down. She didn't go like that. You can see it's flattening out for her, so she's slowing down because of the concavity change there, okay? She's decreasing at an increasing rate. Right here, she's decreasing at an increasing rate, right? Which means she's slowing down gradually. And from there, we are gonna, that's just a basic intro into what definite integrals are. Remember, a definite integral is an area accumulating function. It accumulates area under the curve, and it can represent many different things. It just depends what the units on the y-axis and the units on the x-axis are. And that'll do us. There's no homework. We'll be back tomorrow to start section 5.1. Have a good afternoon.